Assalamu alaikum wa rahmatullahi wa barakatuh. Inshallah, today we are going to implement experiment number 7, which is the bipolar junction transistor common emitter amplifier, the BJT common emitter amplifier. Before we start, I'm going to just show you how the device looks like in the lab, the BJT looks like in the lab. If you go to the lab, and you'll find that the device looks like this. From one side it has an edge, and the other side it's a circular device with a notch or a node here, and then this is how the device looks like. The device has 3 legs. If you look from the top at the device, you'll find that there is a leg here, there is a leg from the back, and there is a leg here. So let's plot this as dotted. Okay, so the legs are ordered as collector. This is the collector leg, which is the first leg if you look from the top. Okay, then this is the base, this is the emitter. So this is how the device looks like in the lab. Okay, and these are the 3 different legs of the device. So the experiment today, we are going to implement the common emitter amplifier. The first step of the implementation today is we are going to implement the DC circuit, only the DC circuit. So the DC circuit looks like this. This is a DC source, 10 volt. This is RC, 3.3 kilo ohm. This is RB1, which is 50 kilo ohm. This is RE, 2.2 kilo ohm, connected to the ground. And then we have the last resistance in the DC, RB2, which is 22 kilo ohm. So this is the DC circuit of the amplifier. Once we implement this DC circuit, we are required to measure some DC measurements. For example, we are going to measure the value of all voltages, V base, V collector, V emitter, and also, so V base is here, V collector is here, and V emitter is here. And then we are required from these 3 voltages to make sure that the transistor is working in the correct amplifier region. So that in order for the BJT to operate as an amplifier, it has to be working in which region? Yes, in the active region. So we have to confirm that the transistor is working in the active region. And how to confirm this from the voltages? We can confirm this by confirming that VCE is bigger than approximately 0.2 or 0.3 volt. So this is how to confirm that it is in the active region. So after measuring the voltage, you have to calculate VCE and confirm that it is larger than 0.2 or 0.3 volt. And this means that the transistor is operating in the active region, and hence we can use it as an amplifier. Also, we'll have to measure the currents. So we need to measure the current in the base, the current in the collector, and the current in the emitter. So we'll have to measure I base, IC, and IE. And also from the currents, you can confirm the famous relation, which says that IE equals I base plus I collector. Okay? And once you do that, let's try to see whether this relation is satisfied or not, and whether there is some errors, practical errors in this relation or not. Okay? Once we finish the DC part, we'll move to the AC part, or the complete amplifier circuit. So I'm going to remove this now. And in order to plot the complete circuit, we are going to connect the base here to a capacitor. And the capacitors that we are going to use in this experiment is electrolyte capacitors, which means that the direction of the capacitor is very important. So you have to connect the capacitor in the direction specified in your manual. And please note that for this specific capacitor, it is wrongly marked in the manual. So you have to connect it, the positive in this side and the negative in this side. And you have please correct it in your manual. And then we connect the resistance called RS, and then we connect here our function generator, where we are going to generate a sinusoidal wave with 100 millivolt peak to peak and frequency of 100 kilohertz. So here you are going to generate a sinusoidal wave of 100 millivolt peak to peak with a frequency of 100 kilohertz. After this, we connect RE to bypass capacitor CE of 100 microfarad. By the way, this capacitor, we'll call it C1. It is 222 microfarad. And then we are going to take our output from the collector and through a capacitor C2, which is again 22 microfarad, and this will be our output voltage, and then we'll have a load resistance here connected between the output and the ground. This is the load of 3.3 kilo ohm. So this is the complete circuit of our amplifier. Once we connect this complete circuit, we are required now to measure some gains. So before we measure the gains, I'm going to tell you that the source or the supply voltage, we are going to call it Vs. This is the supply voltage coming from the function generator. The voltage between this point and the ground, we are going to call it Vs2. So the voltage between this point and the ground, we will call it Vs2, while the voltage coming from the function generator is called Vs. Okay? So now what we are going to do is we are going to measure some gains between the output and Vs and Vs2. So the first gain that we are going to measure, we'll call this AC analysis. The first gain that we are going to measure is A1. A1 is a ratio between V output over Vs2. And then we are going to measure another gain, A2, between V output over Vs. So you will measure on the oscilloscope, you will connect your channel 1 here. This is channel 1 of the oscilloscope. Sorry, this is channel 2 of the oscilloscope. And then you connect channel 1 either between Vs or Vs2. So channel 1 will be connected either here, between this point and the ground, or sometimes you will need to move it here between this point and the ground. So channel 1, sometimes it will be here if you want to measure the gain between V output and Vs, or if you want to measure the gain between V output and Vs2, you have to connect channel 1 here. So channel 1 will be moving between these 2 points. Okay? So you will have to measure A1, which is the gain between V output over Vs2, and when you measure the gain, either use the peak over the peak or the RMS over the RMS. You have to use the same criteria in both. Okay? And I just suggest that you use the peak of V output divided by the peak of Vs2, and here you use the peak of V output over the peak of Vs. And then we'll measure two other gains, A3 and A4. So A3 is defined as V output over Vs2 when the CE is removed, when without the capacitor CE. So what you are going to do is you are going to measure to remove the capacitor CE completely, remove it, and then measure the gain between V output and VS2. This will give you the gain A3. And then the last gain that we are going to measure, A4, it is the ratio between V output over VS2, okay, when we remove the load resistance, without the load resistance, but with the capacitor CE. So again, you are going to connect the capacitor CE once again, and then remove the load resistance. Remove the load resistance means what? Means you completely remove it. You make it open circuit. Okay? And then you measure the gain A4. Now, once we have these four gains, we can use these four gains in order to calculate the value of the input impedance and the output impedance of the amplifier. How to do that? We can do that using these two simple equations. So we have an equation that says that R input over R input plus RS equals the gain A2 over A1. We already have the gain A2, we have the gain A1. We know that RS, the resistance RS, it is, according to the manual, it is 10 kilo ohm. So we know what is RS. So we can use this equation in order to calculate the value of R input, the input impedance of the amplifier. So this is the first equation in order to calculate the input impedance. We have a similar equation to calculate the output impedance of the amplifier. So we have another equation that says that RL over RL plus R output equals A1 over A4. We already calculated A1 and A4. We have the value of RL, and the value of RL in our circuit was 3.3 kilo ohm. So the only unknown in this equation is R output. So we can calculate R output, which is the output impedance of our amplifier. Okay? So when we connect the AC part, we'll measure four gains, A1, A2, with CE and the load connected, and then A3 with the RL connected but we remove CE, and then the last gain A4 without RL, we remove RL but we'll keep CE connected. Once we measure all these four gains, we can use A2 and A1 to calculate our input, and A1 and A4 to calculate our out. I forgot to say something. When you measure the currents in the beginning in the DC circuit, you have to connect the multimeter in series. First, you have to remove the red cable of the multimeter from the voltage terminal and put it in the current terminal, okay? Because the current terminal in the multimeter, if you want to measure the current, there is a terminal that is different from if you want to measure the voltage. So the first step that you should do in the multimeter is that you should remove the current, the red cable from the voltage terminal, put it in the current terminal. And then when you measure the current in the DC part, for example, if you want to measure the current in the base, then you have to connect the multimeter in series. In series means, if this is your multimeter, you have to connect the red terminal here and the black terminal of the multimeter here. This is the meaning of connecting the multimeter in series, okay? And in this case, you will be able to measure the current I base. Now, similar to this, we can connect the multimeter in series with the collector in order to measure the collector current, or with the emitter in order to measure the emitter current. Okay? So this is how to measure the current in our circuit. Okay? Once we do this, we finish the DC analysis part and the AC analysis part, and that's it for experiment number 7. Thank you very much.